Video, we're going to look at the evaporative cooling process on a site chart. So here's our site chart, and here's our challenge. We are going to cool air that is 100 degrees and only has 13.6 grains per pound to air that is 70 degrees. So we're going to start over here, and when you have two conditions, in this case we have a humidity ratio and the dry bulb temperature, you can place yourself on the site chart. And in the case of the dry bulb, that's these green vertical lines you see running here. They run up and down, and you can see the scale, 70, 80, 90 degrees Fahrenheit. This is what you would measure or see on a thermostat or thermometer. This is that condition in here. And then the second one is the humidity ratio. Now, humidity ratio is the measure of how much mass of water there is relative to the mass of the air. And this site chart, we're using grains as the measure of the mass of the water. There are 7,000 grains in a pound, and so we're down here. This is a 20 grain line. You can see the blue lines, they run horizontal. There's 40, 80, 100 grains. So this would say that there are 100 grains of water vapor for every pound of air. That's what it's telling you. We were told 13.6, so you can see we're down here below the 20 line, and now we've established our starting point. And once you get two properties of air, you can plot yourself on a site chart, and you can calculate all the other properties of that air. This is also true of an app or a piece of software. Once you know two conditions, you can calculate all the other ones. So let's go ahead and apply the process. And so here we are. We're going to follow this line here. So what's physically going on? This is a kind of process that's common in desert conditions where the air is very dry. And so you can have very hot, very dry air. If you want to imagine you're in Phoenix, Arizona, this air is 100 degrees, but very, very little humidity in it. If we expose that air to water, the water will evaporate into the air, and it takes energy to evaporate that water. It takes a lot of energy. It takes 1,000 BTUs of energy to evaporate 1 pound of water. And so what's going to happen here, the source of that energy is actually the sensible heat of the air. The fact that it's 100 degrees, it's hot air, it will give up its sensible heat, and we will use that energy to boil the water. And so that will become the latent heat of the water. And what you would see here is that we will you'll see that the temperature drops because we're removing the sensible heat, right? So you started at 100, and then we went to 90 and 80, and then all the way down to 70 degrees. So we've cooled the air 30 degrees dry bulb, okay? But on the wet bulb line, and wet bulb is these blue lines, 40, 50, 60, that run at an angle in here, we didn't change its wet bulb, and we didn't change its enthalpy either, because it is an evaporating process. So you follow the lines parallel through here. And so we started here at 113% RH, cooled the air to 70 degrees, and but we stayed on a common wet bulb line of 60 degrees F and ended up here. So let's look at relative humidity. We could talk about 13.6 grains and 100 degrees. It's actually 5% RH, 4.8% relative humidity. Now our relative humidity lines on the site chart are these sweeping curves through here. So you can see 20, 40, 60, 80. This one here is 100% RH. It's the saturation line. It means that the air has all the water molecules in it can possibly hold. It's not possible to put any more moisture into that air. Now this is a desert condition. You can see that there's very little humidity in this air. It's very dry. That's why it was so readily able to absorb water and convert its sensible temperature in exchange for raising its humidity from here. And we ended up at 70 degrees and 56% RH. So you can see this process is cutting across all the relative humidity lines and raising its RH up as we go. Now, The whole reason that we were able to cool this air was because we used the heat that was in the air to boil water, and that water vapor ended up in the air. So we started with air at 13.6 grains per pound, very dry, and we ended with air that had 61 grains per pound in it. So we significantly increased its humidity ratio. And what do we mean by humidity ratio? Well, that's these blue lines that you see floating across here. And what it is, it's a measure of the amount or mass of water vapor relative to the mass of the dry air. And on this site chart, we're going to measure the mass of water using grains. Now, there are 7,000 grains in 1 pound. It's just a unit of measure. And so what this is saying here is, on this line, is that there are 100 grains of water vapor for every pound of air. We started with air that was incredibly dry. There are very few water molecules in that air. And we exposed liquid water to it. That liquid water converted itself from a liquid to a gas, needed a lot of energy to do that. So it took the heat from the air and lowered its dry bulb temperature, that's crossing these green lines, and significantly increased the humidity. So the air entered the device, the evaporative cooling device, with very few water molecules in it, and it's going to leave with a bunch of water molecules in it, and the water was consumed. We actually raised the humidity here almost 48 grains for every pound of air that flowed through the unit. So finally, what we're going to do is look at enthalpy. Now, enthalpy is a measure of the internal energy of the air. It's the red lines that you see here. So you see 30, and this is 30 BTUs per pound. So how much energy is in every pound of air? And we started here at 100 degrees Fahrenheit dry bulb and 13.6 grains, so very hot, very dry air. And we used the heat that was in that air, the sensible heat. We took it and used it to boil the water. So it had the effect of lowering the dry bulb temperature. We took the sensible heat out, but it never left the air. What we did was we used it to boil water, to turn it from a liquid to a gas. We put that humidity into the air, and so you can see this followed a constant, it's an adiabatic process, meaning that there was no change in the enthalpy from the start to the finish. And so we followed this 26.3 BTU per pound line here. So if you're in a desert place where the air is very hot and you have access to water, Phoenix and the Colorado River, you can use that water, expose it to the air, and you'll get adiabatic cooling from that. And it makes a huge difference. The higher humidity is actually a little bit more comfortable, and so this is a very energy efficient way to cool air, as long as you have access to a water source to go and do that. So that's the evaporative cooling process, and thank you very much.